Good morning, everyone. My name is Ken Lee. I'm Director of Engineering and Research at PHMSA, and I'm going to be presenting more of a high-level discussion about cracks and leaks, mainly about the research side, because that's the area that I cover. So first, I'd like to say, we appreciate all the efforts to develop these two API documents. We realize, that a lot of work went into that, and we appreciate all of the industry work to drive the ball forward. We feel that this provides very valuable guidance and insight to the industry. PHMSA has reviewed the drafts and is submitting comments and feedback to API, as Stuart mentioned. And we will be reviewing the final document. And PHMSA, we, after our review, we may incorporate this by reference. We may not. We may incorporate it by part or the entire document. So, that remains to be seen. To give you some of the background behind all this, recent incidents have highlighted some of the issues that we've had with crack and leak detection. Some of these accidents, ILI tools were run, a crack detection tool were run less than 2 years before the incidents took place and failed to identify the critical cracks which failed. Some of these were criticized for not detecting the leak soon enough and not shutting down the line soon enough. I'd like to say that, cracking is one of the top causes of pipeline failures. Many of these cracks are difficult to detect, especially in older pipe steels that have lower toughness than today's modern steels, and they can be difficult to find with even the state-of-the-art modern crack ILI tools, which we have today. In liquid lines, cracks are more of a concern because we see more severe pressure cycling that can result in fatigue crack growth. And current ductile crack models, they may not predict failures that you may have in some of these vintage brittle steels and seam types. So leaks also pose a big challenge. Small leaks may be very difficult to detect, especially in high volume lines. Some liquid lines can flow over 1,000 barrels per hour, and it may be very difficult to detect a small leak in those lines. And some lines deliver batched products where they may be flowing gasoline one day, diesel another day, jet fuel another day. So that may be difficult, or if the product may vary in that line. And also, some of these lines flow in areas where there's other sources of hydrocarbons, naturally or from other sources. So it may be difficult to pinpoint a leak from that specific line. And this also ties in to the valve closure time, because one of the metrics may be time from leak detection to valve closure. And this may lead into discussions about valve spacing, automatic valves, and remote control valves to try to speed up valve closure times. So this relates to those efforts too. This is one of the charts that's in the RP document, and this talks about some of the methods of leak detection and with the size of the leak which we have. So since we're short on time, I won't cover this but in detail, but they can be ruptures and to very small leaks or seeps. So there can be a wide range of flow rates with leaks. And there's a number of technologies that can be used, external and internal leak detection. This can be continuous and non-continuous methods. So there's a lot of methods that can be used for leak detection. Some of the work that PHMSA has done is we had 2 workshops in the past. In 2014, we have a Managing Pipeline Cracking Challenges workshop. And in 2012, we had a leak detection workshop. So I mean, there are many efforts to address this. That includes rule making, standards development, like these API recommended practices, and research. And I like to focus on the research side. The research side is interesting because it's quite a change from regulations where we focus on penalties if you don't meet the minimum bar. Research is jumping as high as you can, trying to advance technology and understanding. So it's a much different approach to tackling the issues. And I think Jeff talked about our R&D program a little bit about yesterday, but we focus on trying to obtain near-term solutions to impact pipeline safety. And this slide talks more details about that. But we focus on 3 different areas: on developing new technologies, on strengthening consensus standards, and promoting knowledge and understanding of the issues. And I think we showed this slide yesterday a little bit at the bottom, and we have about a $12 million annual research budget for our core program at the moment. And many of the projects that we have focus on cracks and leaks. For crack research, we have over a dozen projects, over $13 million. And for leaks, we have over 20 projects and over $10 million. And the past research has resulted in 3 commercialized technologies that have reached market and that are being used. And here are some of the successes which we have, and you can see many of these focus on cracks and leaks, including what you see on the right-hand side, some aerial leak detection methods using lasers, and some you can see some ILI tools on the left-hand side to improve the technologies for ILI tools that can go in unpiggable lines and to increase the resolution of the state-of-the-art tools that we're using today. And on the bottom left, you see a ball sensor that can listen for leaks as the ball flows through that line. So there's a number of different technologies that we're funding to try to improve. One of the big ones which we have related to cracks is the ERW pipe seam study. Keep in mind that many of these projects overlap many categories. So this focuses a lot on vintage pipe seams as well as cracking. And phase 1 of this study focused on studying and understanding the problem of cracks in ERW pipe seams. There's a paper that's on our website here. You can see the web page there that you could download that has a study of over 100 ERW failures. And also talked about how some of the models used today are not appropriate for all seam types, seam type of defects that we're seeing now. So there's a significant amount of, I think, understanding that was developed in this. And then in phase 2 of this, they're working on solutions on how to address this, including new technologies and ILI tools, pressure test methods, and also full-scale testing to validate and improve models. And there's a lot of lessons learned here, which I won't get into because we're short on time. But I think this has significantly increased our understanding of these issues and to improve the rate of crack detection, preventing future cracks from failing in the future. There's also studies that we're doing on improving in-the-ditch methods, because we're seeing that in-the-ditch defect measurements, they're not as good as they could be. So we're doing work there to improve those methods. And there's a lot of work which we're working on to improve full-scale testing, because this is pretty much the main way to show that your models are working. Is the research, do the real-world test results follow all of the equations and calculations and predictions which you're using now? We have a project on improving leak detection system design, redundancy, and accuracy. So this is one of the many projects which we have now. And I just want to point out that this research is leading to that there's probably not going to be a silver bullet or magic technology that will address this issue. And probably one size won't fit all, because we're dealing with pipelines that can be modern steels, vintage steels, liquid lines, gas lines, class 1, class 4. So there's many issues that we don't think that one tool or technology can address. And research is pointing to using more tools in the toolbox, developing better tools, and how to complementary use different tools to get the results which you need. So to summarize, crack and leak detection are, they remain to be difficult issues which we're trying to solve. There are a high priority for PHMSA. We're devoting a lot of resources and efforts to address these issues. Like I said, one size fits all solution is not likely. That's where the current research, and these are some of the leading researchers in the industry, what they're saying. And appropriate use of multiple tools may be needed, and better tools, of course, to address these issues.